Maxwell's laws, or equations, are four fundamental equations that describe the behavior of electric and magnetic fields, unifying electricity, magnetism, and light, showing how charges and currents create fields, and how changing fields generate each other, forming the basis of classical electromagnetism and leading to the understanding of light as an electromagnetic wave. They explain that electric charges create electric fields. Changing magnetic fields create electric fields. Faraday's law. Currents and changing electric fields create magnetic fields. Ampere-Maxwell law. And there are no magnetic monopoles. Gauss's law for magnetism. A set of four equations that describe how electric and magnetic fields are generated and altered by each other. By charges and currents, Maxwell's laws developed between roughly 1855 to 1865. Key papers were published in 1861 to 1862 and the comprehensive theory in 1865. Maxwell was a professor at King's College London. To unify existing, separate theories of electricity and magnetism, by Faraday, Ampere, etc., into a single, cohesive theory of electromagnetism, and to mathematically explain light, Maxwell analyzed Michael Faraday's lines of force and used advanced calculus to create a mechanical, fluid analogy model of the electromagnetic field. He notably added the displacement current term to Ampere's law, which allowed for the prediction of electromagnetic waves. Electromagnetic waves travel at the speed of light, laying the foundation for modern telecommunications, radio, radar, optics, and electrical engineering. Gauss's law for electricity, formulated by Carl Friedrich Gauss, published 1867, states that the total electric flux through any closed Gaussian surface is proportional to the enclosed electric charge divided by the permittivity of free space. It relates electric fields to charge distributions, simplifies calculating fields for high symmetry, spherical, cylindrical, and is expressed as 2. Gauss's law for magnetism states that the net magnetic flux, phi b, through any closed surface is always zero, mathematically expressed as. This fundamental principle of electromagnetism signifies that magnetic field lines form continuous closed loops and that isolated magnetic monopoles, single north or south poles, do not exist. Examples and applications. Bar magnets. If a closed surface is placed around any portion of a magnet, the total field lines leaving from the North Pole equal those entering at the South Pole. MRI machines. Medical scanners operate based on the principles of strong magnetic fields described by this law. Earth's magnetic field. The dipole field of the Earth follows this law. 3. Faraday's law of induction states that a changing magnetic field through a coil or closed loop induces an electromotive force, EMF or voltage, proportional to the rate of change of the magnetic flux. It explains how generators, transformers, and electric motors operate by converting mechanical energy into electricity. Applications. Generators. Convert mechanical motion into electrical energy. Transformers. Increase or decrease AC voltage levels. Induction cooktops. Generate eddy currents to heat cookware. Electric guitars. Use magnets and coils to convert string vibrations into signals. 4. The Ampere-Maxwell law is a fundamental equation in electromagnetism that states a magnetic field is generated by both electric currents, Ampere's original law, and changing electric fields. Maxwell's crucial addition, the displacement current, unifying electricity, magnetism, and light into a single theory of electromagnetism, and predicting self-propagating electromagnetic waves. It explains how a varying electric field, even in empty space, like between capacitor plates, acts like a current, creating a magnetic field, which is essential for understanding electromagnetic waves and light.